That's badly drawn. We'll try that one again. Is that thing still running?
Oh yeah, still running.
Okay.
We stop.
Stop. No, don't stop it. I just wanted to make sure, because it usually stops on its own about this time. I think I figured out part of the secret is I need to start it, hit pause, and then hit play. Because if I just hit start and it goes, that's when it seems to stop after 22 minutes and whatever seconds. All right, so the second harmonic, or sorry, the next harmonic, it's not the second, it's the next harmonic. Better, still not great. How many waves is that?
3/4.
This is the third harmonic. Second harmonic doesn't really exist here. Or it's the first overtone. Which I think is why they use the term overtone, is just so that you can go sequentially. And then the next, let's go for the fifth harmonic. So we'll add a wave each time. Yeah. Those are supposed to be the same size, and that's supposed to be half those. How many waves?
1 1/4.
And so, over here, so the wavelength is 3/4 the length, and the wavelength here is
5. 1 1/4. So that's 5.
the length is 1 1/4 waves, but what is the wavelength?
4/5.
So 4/5.
Okay, 4/5 is the length. All right, so let's make
It's
it.
on the third harmonic, so it's supposed to be flip flop.
Oh, yes, it should. Yeah, thank you. Any other carols there? Not so far. Therefore, let's make our predictions. Speed of sound should still be about roughly the same. It should be
42.
344.441.
442.
442 meters per second. All right, this time we know the frequency, or at least we're trusting the frequency. Frequency is 512 hertz. And so I know the speed is equal to the frequency times the wavelength. And so the wavelength should be the speed divided by the frequency. So 344.442 meters per second over 512 hertz gets us what? Point 8 something? I guess we'll all find out.
I got 0.6727.
0.6727 units?
Meters.
meter.
Yeah, I hope so. Remember that hertz is per second. It's basically oscillations per second. So we have meters per second over oscillations per second. Divided by a fraction, the same as multiplied by the reciprocals. That's meters per second times seconds per oscillation. And so meters per oscillation, or just meters, wavelength. Now what should happen here is if I'm not at the, in the last step, I know what the wavelength is, so the first harmonic should occur at what length? If my wavelength is 0.6727 meters, at what length should my column be, air column be, in order to hear it?
1/4 of
Oh, that's
0.6727.
Which is around 16 centimeters.
16.8,
818. All right, meters. And that's more precision than I can see with my naked eye. Now, one thing to note here is that 0 is not at the very top. And occasionally I get a clue, and I think I'm on to why they did this, and I'm still not sure. But 0 is actually 2 centimeters from the top up here. So,
because they want to be annoying.
yeah, my best guess right now is that 2 centimeters is because they originally probably had 0 at the top, and there were some issues with it sliding, and that gets all messed up, so they put it 2 centimeters below it and expect me to cut that off. Not 100% sure, but they were all consistent that way, of the new ones. The older ones were not like that.
So we have to subtract 2 centimeters.
So whatever we get right here, we need to add 2 centimeters. So 16.81 centimeters, that's where it is on the measuring tape here, but since I have the 2 centimeters right there, I would expect it to be right there. Oh, you said subtract, this is what you're subtracting from. Well, subtract from that. Yeah. I was thinking whatever this reading is, you would add 2 to get it. So I would expect the first harmonic to be somewhere around there. Now that first harmonic, we got a wide gap right here. This is where it's vibrating the most, so it should be louder when we actually hit the harmonic. Matter of fact, the first harmonic should be the loudest. And I'm realizing that we are gonna need some water. Get up with that. Now, in order to change the level here, we basically are gonna move this up and down. And if we do it right, we're gonna get metal and metal scraping. So notice that this is dropping, and this will drop until the level on the tube is the same level in the reservoir here. Beyond the scope of this class, but not beyond the scope of physics. And I need to add some water because I need to get it higher than what I had right there. Now, when doing the first version of this experiment, the experiment that you'll end up doing tomorrow, in the first version, you were getting down to the harmonics down here, so to have enough water in here in order to get the first harmonic generally means you have too much water to get a harmonic down here, and so you generally need some sort of receptacle to quickly dump water in if you need to. So just lift this should go up high enough. When I get closer, I'm gonna hit this.
You have a piece of metal you can tap it with?
All right, so now that you bring that up, never do metal on metal like that. If you look at the older ones here, there's dings all along it. That's because somebody smacked it with metal. What we do have, and yes, it gets a great sound, but it does damage. It should be back here.
A wooden mount.
You have a piece of brass? What's that made of?
We have our strikers here. Fingernail usually works well, I'm just awkward.
You'll tighten that thing down.
Why don't I bring where I can actually get to it better? There you go. You got louder there? All right, this seems to be loudest right where my thumbnail is. All right, and my thumbnail is at 14.2.
So, pretty close.
Yep, pretty darn close. So, not too far off. Let's see how well. Now, one of the issues with this lab is there's some false harmonics. It's loudest at the first harmonic. As you work your way down, it would be loudest at that point. However, let's see how high up we can get this. Now strike it again, and assuming it's quiet enough. The other issue I'm having right now is that the tube at the bottom is getting kinked and not allowing free flow of water. So let's get it back up again. Now let's see if we can hear the false harmonics. Not hearing it there. And that's
I
the
heard
first
it
harmonic.
there.
First harmonic. Not happening now. I wonder if it's a different frequency than where it tends to happen. So let's try a different frequency. Actually, let's hit the other ones and then we'll try the other frequencies. All right, so the next harmonic should happen at, well, when the length is 3/4 of the wavelength. So where could that be?
.504525.
0.504.
525.
Appreciate the level of precision people are given. Or perhaps it's just fate that I can recognize down to the micron. All right, so that's gonna put it down here, so let me get it closer. Really subtle there. My hearing's going completely. Alright. So my thumb is at the 47 centimeter mark plus the 2 centimeters. So that puts us at 0.49 meters. So we're 2% off. So let's try a different frequency.
What is the, tuning fork made of?
Say it again?
What is the tuning fork made of?
I don't know. I assume aluminum, but it's relatively light.
As aluminum. If I was steel, I would say use an aluminum rod or something to hit it. Because aluminum wouldn't do much to steel, but if it's aluminum, then use a pencil.
Yeah, actually, pencil might be the way to go, something not metal.
Oh, yeah.
Oh, that's not bad. I'm feeling confident that that plastic's not gonna do much to this. All right, this is 256 hertz. So let's go for another color. The markers. All right, so 256 hertz. So that changes to 256. So what happens to my wavelength?
Get cut directly in half, I think. No, it's gonna double.
Yes. So 1.3454. If I doubled that correctly.
It's 1.345476563.
So with rounding, 5.5. So a quarter of that. Should just be double what I just raised to 0.336 something.
Um, three, 6, 3, 5.
All right. So the first harmonic, we should hear the first harmonic when it's in this region down here. Oh, and there's a pencil. How does that work?
About the same.
I think I'll go for the soft wood, or the wood. Let's get closer. Give time for the water to get up there. Right there. I don't know if you heard that.
And louder.
That's the first harmonic. Not quite as distinct as the last one. My finger is somewhere around the 0.31 meter mark. And we predicted a little over 0.33, so when you add the 2 centimeters, pretty darn close. Now, let's see if I can get the false harmonic on this one. Let's get it going. Surely it's not my dream.
I heard it.
There. So that's about 15 centimeters from the top. It's roughly half this value right here. Half this value right here-ish. And so that was messing people up because I've changed the lab, but if you view that as the first harmonic, then when you get down to that value, you're basically hearing what you're really is the first harmonic, you're interpreting as the third harmonic, and it really messes with any type of analysis you're going to do. So on this type of lab, when you use the tuning fork, it is okay to sort of have some idea about where it's going to land, about what roughly where it's supposed to be. It's pretty much the only lab where you really, well, you should never do it, but with something where it requires your hearing involved, it gets a little funky. So.
Quick question.
Yep.
What note is that on a piano?
That is a C. At least that's what it says right there. Is that what you were hearing?
No, I just wanted to ask.
The 512 is also a C. Let's see, that's 512 also. This is 384 hertz. That is a G according to this. All right, questions up to here?